here's the topic. We're going to take a look at the next chapter. This chapter, what it does, and what kind of prepares us for the grand finale of chapter 3 is the stuff I've talked a little bit about before. It's called optimization. And we're going to take some mathematical or some applied mathematical situation. Maybe it's an economic situation. Maybe it's a physics situation. And when we've got some variables that are related, we're going to use calculus to optimize variables, optimize quantities. You know, the classic example would be if we've got something like profit as a function of the number of widgets that we're selling in our calculus business, then we want to look at the relationship between those variables and use calculus to find out what's the number of widgets that we want to sell to optimize profits, maximize profits. So optimize means maximize or minimize. Sometimes you want to minimize things. Minimize costs. There you go. But we got a little ways to go before we get there. Okay, so we got some skills to learn and some things to practice. And the first thing we're going to look at in this introductory section here is really just some terminology. We're going to want to get the language of this type of calculus, get comfortable with that. And we're going to look at some rudimentary examples. Now, these examples are going to be really very common sense kinds of things. You'll anticipate what to do with the calculus. And then later on, we'll look at some tricks and techniques that we can do to really trim this down and make it more efficient and take some big shortcuts. So first of all, we're going to talk about extrema today. And extrema are just nothing more than the extreme values of a function. So the highest and lowest values. Y values. Okay, so if we've got, let's let f be, some function f be defined on some interval. Okay, we don't need to be talking about the entire function. We're just talking about, locally speaking, on some interval that we're interested in, call it I, containing some point, some x value c. Then we would say that f of c is the minimum of the function if it's the smallest value, it's the smallest y value. If f of c is less than or equal to f of x for all the other values of x surrounding c. If c is the one that gives us the smallest y value, then doesn't that stand to reason we might call that a minimum? Okay? And then conversely, if we call f of c a maximum of the function if for all the values of x around this one value c that we're interested in, if f of c produces the biggest y value, then we'd call it a maximum. And so if we were to draw a picture, the picture would be really pretty simple, right? Picture would just look like this. This board changed on me. This is having issues. So let's say if this is our function and this is our interval. Say we're going, I is going to go from about there. That's all we really care about. We don't care what the function is doing elsewhere. But on that interval, if the function does something like that, then wouldn't you say that for that value c right there, on that interval, that's the biggest y value? Yeah. So it's a maximum, right? What's a maximum mean? A mountaintop. Topologically speaking, it's a mountaintop, right? If we had a different function that looked like this, then this could be a different value of c. That's the blue c, and that's a minimum. What's a minimum mean, topologically speaking? And when I say topologically, what's it mean? Ocean crevice. Okay, I was going to say valley, but that's even better. Ocean crevice, an abyss, trench, I guess they call them. So, and that word topological, that's a math word, believe it or not. That comes up a lot increasingly in math. Topologically means when we're looking at the topography of a function, literally has to do with what are the features of the function. And these features sound very map-like, Peaks and valleys sound very map-like, but later on, hopefully you'll continue with math, there's some other strange topological features that you talk about, like rings and enclosures and all kinds of weird things. But it's literally the way the function looks, or the relation looks. Okay, so types of extrema, then. Well, I guess I'm jumping ahead maybe just a little bit here. The book throws something at you called the extreme value theorem. Very common sense. This is what we call an existence theorem in calculus. It's an existence theorem because all it says is that if we meet certain conditions, then something must exist. In this case, an extreme value. If a function is continuous, meaning what? What's our simplest definition of a continuous function? Okay, no, in fact, yeah, if I were drawing it on the board, I wouldn't have to take my pen off the board, right? My pen could stay on the board the whole time. And it's a function, so there's no, it passes the vertical line test. If f is continuous on a closed interval from a to b, now, okay, remind me, what's closed interval from a to b mean? As opposed to open interval. Include the endpoints. So I'm putting my pen down at x equals a, I'm going to draw on the board till I get to x equals b, and then I can take it off. Okay? Then, if that's true, so if I've got this function I can draw continuously on the board from a to b, then f has both a minimum and a maximum on the interval. Well, duh, it has to, doesn't it? How can it not? How can I draw a function up there that doesn't have a point that I can look to and say either that is the highest point or it's the shared highest point? Maybe it's a tie, right? Maybe there are two mountains that both get to exactly the same elevation, but I can still point to those discrete mountaintops and say those are the shared maxima, right? So there has to be, obviously in that situation, I have to have a highest point and a lowest point, okay? And those are what we're going to call extrema. So how do we classify these guys then? We're going to look at these in a couple different ways. A relative extrema, relative is a loaded, important word in math. Relative meaning relative to the stuff around it. So we also say in math, locally speaking. If an ant is walking around on the function, he's not carrying binoculars. He's just looking not way out here, just around him, right? In the vicinity of him. We'd call that a local maximum, or a relative maximum. Relative to the terrain around him, it's the highest. But it could be that out here somewhere there's a higher mountain. Is that still a relative extrema? Yeah, because it's still a mountaintop. Is that a relative extrema? Sure, just a higher one. But relative to the topology around them, they're the highest points. So relative extrema, there's a valley, there's a relative maximum, there's a relative maximum, there's another relative minimum. These are what we call topological because they are based on their peaks or valleys, always. They're the shape of the function is what we're interested in. Okay, now, questions on that? So relative extrema are peaks and valleys. Simple as that. The shape, it indicates that they are a maximum or minimum based on how the curve is drawn. An absolute extremum, singular would be extremum, plural extrema. Absolute extrema are defined in terms of an interval. So now if we're going to say, okay, from x equals 0 to x equals 10, what is the highest value of the function? What's the maximum value of the function? What's the minimum value of the function? So if I do something like that, let me draw you a little different picture. So let's say we're going to start this thing right down here. There's the left edge of our interval at A. And here's the right value. Just kind of by eyeballing it here, could you sort of estimate for me where's the absolute minimum on that? Just describe it on that interval from A to B. Closest to A, kind of at the bottom of that valley. Okay, good. So we could say that is relative minimum. And pretty obviously, where's the relative maximum? Now, because we're talking about a closed interval, we could say that in addition, on this interval, this is our absolute minimum, and this is our absolute maximum. Those are, absolutely speaking, there is no, there's no relativeness about this anymore. On that interval, that is the lowest point and that is the highest point. So those are absolute extrema. Now let's scoot this point over a little bit. Scoot this point B over so it's not here anymore. let's put it out here. Oops. What does that do? Changes the absolute maximum, because now the right edge of this, the right boundary of this interval includes this infinite upslope, doesn't it? And it cuts us off right there. So now this is still a relative maximum, isn't it? Because it's a peak. But where is the absolute maximum on our interval? Aha, yeah, the absolute maximum is now right there. Make sense? See the difference? Okay. And then we say the last one is we don't really use it that much, honestly, but you'll see it. I guarantee you'll see it at some point in your math careers. A global extremum is just a combination of both. A global extremum is it's a peak or a valley that is, no matter where you go on the function, it's guaranteed to be the absolute maximum or minimum. Can we think of an example of a function where we might see something like that? Parabola. Yeah, parabola. Sure, exactly. If I take the function y equals x squared minus 6x plus 9. So we look at something like that. Then where is there a global minimum? Yeah, down there at the vertex, right? Yes. Makes sense? Because this function, it's always opening up, right? And so that's guaranteed to be, no matter where you go, no matter what interval you impose, if it includes that point, that's got to be the minimum, right? So global just means, it's a valley or a peak that is, absolutely speaking, the lowest valley or the tallest peak. Yes, sir. You're right. There is no global maximum. You're right. And we could have an absolute maximum if we artificially enclose the interval, but otherwise, you're right. Yep.
Is there no relative maximum?
There is no relative maximum. Okay. Right. Because there's no peak, is there? Right. Good. Okay, so we're going to look at a couple examples. Now, okay, before we go hunting that's what we're going to do today. We're just going to go hunting for relative maximum and minimum. That's what we do a lot in chapter 3. I have to introduce you to another character in our cast here. Relative extrema, so peaks and valleys, always occur at critical numbers. Is how we're going to call these things. Critical meaning special or heightened importance. However, we're going to learn how to find these critical numbers. Lots of critical numbers are false alarms. So it's not a two-way street. All relative extrema occur at critical numbers, but not all critical numbers produce relative extrema. Does that make sense? Okay? It's like saying all chickens come from eggs, but not all eggs hatch, right? Something like that. Not a great example, but you get the idea. So now if we think about this, if we think about this now, just from sort of a general qualitative perspective, we can probably come up with, without even cheating and looking at there, but we can come up with where we would look for critical numbers. Now, relative extrema are peaks and valleys, right? So we want to find peaks and valleys. Think of the kinds of places where peaks and valleys might exist. Where might peaks and valleys exist? Let's do this. Oops. Let's do this real quick so we can just think about this on our own for a second. Now thinking about the first derivative, okay, and I'm going to make some general statements that are going to be pretty cryptic right now, but as you use this more and more, you'll kind of get a feel for this. When we analyze functions, what we're going to do is we're going to look at values for the independent variable. We're going to look at values of the function, values of the first derivative, and eventually values of the second derivative. And the further down that chain we work, so the further we get from a regular function towards a second derivative, the more efficient it is, the more information is hidden in the picture. Okay? And so right away, we're going to jump off of the regular function into the first derivative. Okay, now think in terms of the first derivative, how could that help us in finding topological features, peaks and valleys, extrema. What's going to happen? Can you tell me about certain behavior of the first derivative that we should be looking for in a peak or a valley? Yeah, I'm just going to draw one up here so you can kind of stare at it. Let's take a peak and a valley. And we'll take smooth variety peaks and valleys here at first. We can look at smooth or jagged. Give it smooth ones. So we're interested in this point right there and that point right there. Anything interesting happening with regard to the derivative at that point?
There's only one. Let me check for that. Because that would be like x cubed and the derivative would be x.
Well, okay, yeah, but forget about the specifics of the function here. I could draw any function. That's irrelevant. I'm just looking at can you tell me now, think derivative-like here, right? Remember, we got to put ourselves back in that frame of mind. Derivatives are slopes, right? So the value of the derivative function equals the slope of the curve. So what's going on? Can you tell me what's going on there at those places, at the peak and the valley? What's special about the derivative? It's zero. Yeah. It's horizontal, isn't it? Those are horizontal tangent lines. And so for a smooth function, it's a rounded peak or a rounded valley, which, it's hard to say it's usually, but in math, most examples you look at are like that. Then we're just looking for a zero derivative. Now that's convenient for us because finding zeros of functions is something that we're pretty good at. We spent years and years and years studying and practicing finding zeros of functions, right? So there's one type of critical number that we're interested in. I'm missing some good stuff. This is so messed up. Okay, so there's one where it's hard to see, but that's an f prime. So f prime of x is 0. So the function has a horizontal tangent, right? Because it has to. Now imagine the ant walking along the function. As he clears, just passes the crest, or just hits the valley, he's going to stop going uphill. If he's walking up a hill, he's going to stop going uphill, and he's going to momentarily be walking horizontally, just for a split second, right? When he hits the bottom of the valley, he stops descending. Before he starts ascending, he bottoms out, he levels out. Okay, now what about the case of a jagged peak or a jagged valley? Those are also peaks and valleys. How am I going to use the derivative to identify that guy or that guy? What's going on there? Can you tell me what's interesting about the derivative there? Doesn't exist. How come? Sharp corner. Okay, so now that's kind of an odd answer, but it's still an important way of analyzing things. Every place else the derivative is fine on this function except right at that peak and right at that valley. So places where the first derivative is undefined could also indicate places where we've got sharp peaks or sharp valleys, right? And so that's our other species of critical number. Whoops. Okay, so where f of x is x prime of x, excuse me, is undefined. Now there could be false alarms. We could have places on a function where the first derivative is 0, but it's not a peak. Anyone want to try to draw one? Brave souls. Okay, that we could. That would work. How about something like this? So we're going to come to call that a point of inflection. Isn't that a place where the tangent line's horizontal, but the function doesn't actually turn, does it? It's not a peak or a valley. So that would be a case where, even though the first derivative is 0, not a peak or a valley, how could I draw a place where the function is undefined? The first derivative is undefined, but it's not a sharp peak or a sharp valley. Okay, seeing some. There's one possibility. What if I just had something where it went like, say, like that? It's hard to see that is a relatively sharp corner, I guess, right? But it didn't end up being a peak. Or I could get stuff where, what if I had one like this? Let's say it went. Why is the first derivative undefined there? Vertical tangent line, right? Can be undefined there, but clearly that's not a peak or valley. I could have a break in the function. There's other things that could happen, right? So there are lots of ways we could get false alarms. All right, so let's try this. Let's just take a problem and see if we can go hunting for absolute extrema on an interval. Find the extrema of f of x equals 3x to the fourth minus 4x cubed on that interval. What do you propose we do here? Take the derivative. Sure, let's take the derivative. So what is our derivative? 12x cubed. Okay, now we've got our derivative. Let's just look for critical numbers, right? We got two questions we've got to ask ourselves. Where is that derivative function undefined on our interval, if anywhere? And where does it equal 0 on our interval? Now, first of all, is that function undefined? And let's ask ourselves, where could a function be undefined? Where would a function be undefined? Well, what kinds of things are happening? Okay, but I got to divide by 0, right? If there's some place where a certain value of x would cause me to divide by 0, that's a place where it could be undefined. There's really only one other classic place that we look for things to be undefined. And only two rules for real numbers we really have to obey. You can't divide by 0, and you can't even root. An even root of a negative number. Now, are we in danger of doing either one of those things with this function? No. There are no x's in the denominator, and there are no even roots. So there's no chance of us having a critical number where the derivative is undefined. We can just forget about that one. But potentially it could be equal to 0, right? So to find out, we just set the derivative equal to 0 and do some algebra, right? So how do we solve this equation? Okay, take out a 12x squared, leaving us with okay, so we got it factored. So what are our critical numbers then? X equals 1, or we got another factor here. 0, right? Right? Okay, so those are my two critical numbers. Now, if I'm just looking for the, and what I really should have written there is absolute. I'm looking for the absolute extrema on this interval. Now, let's just be logical about this. Are those guaranteed to give me relative extrema? No. But could they? Yeah, they might, right? So if I wanted to go hunting for places where the function had its biggest and smallest values on this closed interval, what are the values? There's an infinite number of x values on that interval, but I can whittle it down to a discrete number of possibilities that could give me the maximum and minimum values. What would they be? So on the interval from -1 to 2, it's a closed interval, right? So including the endpoints. What are the only candidates? What are the only places that could give me relative extrema? 0 and 1. Okay, because those could be peaks and valleys. Those could be relative extrema. Maybe they are, maybe they aren't, right? But if they aren't, oh well. If they are, they're going to give me back a big or a small value. What are the other places? If we want the highest y value and the lowest y value on an interval, say it again. There's no -2, but and the endpoints, yeah. Yeah, there you go. Good. Could be the endpoints too, couldn't it? Right? Because wherever we stop at the endpoint, maybe it's on one of those big slopes that's infinite slopes like we saw before, right? So we just have to try those 4 values and see what the winner is. So let's just make a little table and see. Now I'm going to have us make our tables for future reference. We're going to make our tables so the x values mirror the x-axis, because what we're going to eventually do is we're going to build these tables at the bottom of the page, and we're going to use the information from the rows on the tables. We'll have one row for the x's, one row for the y's, one row for the y primes, one row for the y double primes. We'll be able to use that information and just kind of move upward and say, aha, based on the table, there's going to be an inflection point. There's going to be a maximum. And so we can sort of sketch a curve based on the information on that table on the bottom, right? So in this case, our table might look like this. We've got x, and we've got y, and we've got y prime, right? When we put our values in, our endpoints were at -1 and +2. So we're going to put the closed brackets around those. And then we found some interior critical numbers. So we had a point at 0 and at 1. And these were places where the first derivative had a value of 0, right? So lining up with those in the y prime row of our table, we can see that tells us that those are horizontal tangents, right? And for now, all we're doing, this is very rudimentary. We're going to get a lot better at this real soon. But for now, all we're really looking at is we're just comparing the y values, right? So we'll just take each of those 4 numbers, and we'll plug them back into our original function, which was 3x to the 4th minus 4x cubed. And we'll see who the winners are, right? If I plug in x equals 0, what do I get back for y? 0. And notice that we'll take that to be an ordered pair, right? X equals 0, y equals 0. What if I plug in 1?
0.
-1. Okay. What if I plug in -1? 7. Do you see that? Because that's going to make this term positive, right? What if I plug in 2? So 48, right? 2 to the 4th, 16. So 48 minus 4 times 8? 16? Okay. Okay, so what is the absolute maximum of that function on that interval? Where does it occur, and what is it? Yeah, it's right there, isn't it? This is absolute maximum, right? Where's the absolute minimum?
Yeah.
See how that works? just gonna, we're just gonna compare the functional values of the endpoints and all of the critical numbers we identify. Now later on, we'll get better at this, and we'll be able to identify without having to plug in, to evaluate the function. We'll be able to tell which one actually is the maximum, which one's the minimum, just based on some other stuff. But for now, we're just gonna plug them into the function and see. Okay, let's try another one. Okay, time for another one? Maybe one more. Okay, how about, oh, that's, okay. Yeah, that's good. Okay, so what are we going to do? Take the derivative. So what's our derivative? Okay. So now if I want to write that, a lot of times when you're analyzing functions, I think it's easier to write a negative exponent actually as a fraction. Put that in the denominator. So we could write that instead as 2 minus 2 over x to the 1/3. The cube root of x. Yeah. Okay, so now let's find critical numbers. So there's our derivative. So let's look at both kinds. Where is our first derivative undefined, if anywhere? Okay, yeah. How come? Good, because here is the danger zone, right? If we're looking for places where a function is undefined, we said that the prime culprit is going to be where we're dividing by 0. And so look at this guy right here. Now, where is x to the 1/3 equal to 0? Because wherever that equals 0, x to the 1/3 equals 0, that thing's got to blow up. You can't have 0 on the bottom. Well, x to the 1/3 equals 0 when x equals 0, right? And if I wanted to prove that, all I would have to do is just say, okay, if I solve that, x to the 1/3 equals 0. If I cube both sides, I'm just going to get x equals 0 cubed is 0, right? But we didn't have to do that. So we know x equals 0 is one critical number. Okay. Where are we going to find the rest of them? Set the derivative equal to 0. Okay. So the derivative equals 0 when this function equals 0. So now we've got to do a little algebra. So what are we going to do to solve for x there? A bunch of different things we could do. Okay, subtract 2. Or how about if we move this term over because it's negative? So 2 equals 2 over x to the 1/3. Now what? I'm hearing lots of good suggestions. Somebody raise your hand and give one of these. Grace? So I'm cross multiplying. Okay, cross multiply. That's fine. Or I could just flip both sides. Either way, if I cross multiply, I'm going to get 2x to the 1/3 equals 2. So x to the 1/3 equals 1. So so the cube root of x equals 1, right? Now here's where we gotta just be a little bit careful with this. First of all, what's the answer? You know the answer. What's it gonna be? It's gonna be 1, isn't it? because only the cube root of 1 equals 1. Now, if that had been x to the 1/2 equals 1, let's see. No, we would have been fine there too, wouldn't we? If we solve this though, the answer is 1. Here's how we can solve this. I'm going to remind you of something, just so we build in a little quick algebra review. In order to isolate x there, I've got to take both sides to what power to make that an x? Third. Okay. Now, whenever I take both sides of an equation to a power, remember that it's a perfectly okay method in algebra, but you introduce possible extraneous solutions when you take both sides to a power. And so the moral of the story is whenever you do that, when you get answers, you have to go back and check them in the step prior to doing that, right? So I always change colors when I do that. So I'm going from purple to 1, or to purple to blue, because now I cubed both sides, right? And then I only get one solution, but to check that solution, I got to go back and see if it works there, and of course it does. Okay, make sense? Okay. So, all right. So we got a critical number then at 1. So we got x equals 0 and x equals 1. Let's go check the values of our function. If we make our little table, what was the interval? -1 to, remember? -1 to 3, okay. -1 to 3, and we got critical numbers at 0, didn't we? And 1? Okay, and those were places. Now at 0, what was y prime? And here it was 0. Okay, now that's important that what that tells us when we see an undefined first derivative, that's telling us sharp peak or sharp valley. This is telling us smooth peak or smooth valley, right? And then we'll just see which y values, which one's the winner. If I plug -1 in, what do I get? That's going to give me -2, right? First term. Now, what's -1 to the 2/3? If there's a 2 on top, it's an even function, right? Because that's really just the cube root squared. When I square something, what's that do to the value? Positive. Yeah, positifies it. There you go. Okay. So then I'm going to get -2 minus 3 times +1. So just -3. Okay, what about at 0? Good. At 1? And at 3, oh yikes. 3 is going to give us something weird. 3 is going to give us, what, 6 minus 3 to the 2/3? Oh my gosh, really? That's going to be, it. The whole thing is? Okay, roughly 0.24-ish. Okay, so it doesn't matter. It's neither the biggest nor the smallest anyway, right? So what's our winner? What's our relative maximum? 0, 0, right there. And excuse me, that's our absolute maximum, isn't it? It's also a relative maximum, though, isn't it? Yeah. Right? How do we know it's a relative maximum? Yeah. Well, no, it's not smooth. It's jagged. But look, if the values around it, if the y values around it are smaller than this one, right, and this is a critical number, doesn't that mean it has to be a peak? How about that? Okay, and then here's our absolute minimum. How about that? Okay.